All right, so in this video, we're going to take a look at a couple more examples dealing with triple integrals. And in this first example I have up here, the first thing to notice is that we're just computing the volume. And so for the volume, much like the area now, you're going to have this triple integral over closed solid bounded region T. And instead of having an actual function sitting out there, you're just going to have the dv. Which, if you remember, that's just some combination of the dz dy dx or dx dy dz or whatever. So we're just going to have the dv out there with no additional function. So to find the volume bounded by all of this, it's probably tempting to think that we would want to start with z, when in reality I think it's a little easier to hold off on that. And you'll see why here momentarily. So to get this set up, we're going to have the triple integral, and I think it's probably easiest to start with the x. I noticed that from this guy right here, x would equal 1 minus z, and then from this guy here, x would equal a 0. So if we started with x, then picture this, and I realize that we're talking about a higher dimension here, but just kind of picture this in its most basic form. You could picture this as a line or kind of a plane, if you will, coming down, and then x equals 0 being something like this. So again, this is very, very informal, but we've got some sort of line or plane, and we've got some sort of x equals 0. And so from there, the top and the bottom are a little bit more apparent. So if I go this route, my x on top could be a 1 minus z, and my x equals 0 could be on the bottom. So we always want to put the big over the little, or top and the bottom. Now, earlier I said it's tempting to start off with this guy, but once we have the x taken care of, now this is all that we have left. And that's good. That's a good thing, because if I look at this now in R2, where this is the y-z plane, then one of my parabolas, or one of my graphs, is a parabola that opens down, shifted up 1 unit, and the other one is a parabola that opens up, shifted down 1 unit. And so this now is our region. So one of the most important takeaways from triple integrals, and this will be the case throughout, is once you get this first iteration done, then it goes obviously down to a double integral, and everything that you've learned in the past comes into play. So this guy is kind of the new idea, whereas everything else now puts us back into our region in R2, and beyond that, there's nothing else new that you have to worry about. So if this is what we want to study now for these last two, I would probably consider going in the order of dz dy. And I say that because, again, we're solved for z. The one that goes, let me sketch this in here vertically, the one that goes on top would be the one that opens down. So now we've got a z equals 1 minus y squared. On the bottom, we've got a z equals y squared minus 1. And then this would scan from right to left from where these two things intersect. To figure that out, I'll take the 1 minus y squared and set it equal to the y squared minus 1. This gives us 2y squared equals 2, or y equals plus or minus 1. So this is going to be our negative 1, this is going to be our positive 1, and of course those would be y values. Y equals negative 1, y equals 1. So when it comes to deciding the order in which you want to do things, remember, just knock out the first one, and in this case it was easiest to go this way, but the motivation for deciding that was understanding that if I knock out the first one, the last two are going to be exactly the same as they were in the last couple sections, and having been given these equations like we have, it really makes defining this region much, much easier for these last two integrals. All right, so now we're going to take a look at an example where we're given this triple integral in a very specific order, dx, dz, dy, and they want us to now convert this to dz, dy, dx. So much like we did in earlier video with double integrals, first thing I would do is identify what all of this stuff is. And so the first thing that you can see on the outer integral is that y would equal 4 and y would equal 0. On the middle integral, z would equal 4 minus y and z would equal 0. And on the innermost integral, we'd have an x equal square root of z and an x equal 0. Now, our job is to come up with a triple integral, f of x, y, z, in the order of dz, dy, dx, which means that these would need to be z equals, these would need to be y equals, and of course these would need to be x equals. Now, to do this, I'll start with my z right here, and I can see that from what we've been given right here specifically, that z would equal x squared. Now, we've got z equaling x squared, and we've got z equaling 4 minus y. So one of these is going to go on the top, and one of these is going to go on the bottom. Now, again, if you view this very loosely, very informally, as the parabola that opens up, something like this, and then some line with a negative slope. And again, I realize we're in different dimensions, but this is the best way to visualize it very intuitively. So if you've got this parabola looking thing and you've got this line looking thing, then it's going to be easy to see that the top part would be that line and the bottom part would be that parabola. So I'll go ahead and I'll put a 4 minus y on top and then an x squared on bottom. Now, in terms of the y, so for the y, we need to be a little bit careful. We know that a few things are in play here. We know that y equals 4. We know that y equals 0. We also know that z equals 4 minus y. And that's going to be important because remember, once you get this first one done, now you're looking to visualize the region in R2. So having already taken into consideration that z equals x squared, now I'm also going to have to take into consideration that my x squared can be plugged in right here. So maybe I'll move this down. And so I'll say that x squared equals 4 minus y, and y equals 4 minus x squared. So if I focus on this for just a second, come over here to the side, I'm in my xy plane. Here's the parabola. Shift it up 4 units, it opens down. And this intercept is a 2. You can see that if you let y equal 0, x would end up being 2 right there. And that's actually really interesting and important in all of this because when we look at the other given information, the fact that y equals 0, y equals 4, so y equals 0, and then this guy would be where y equals 4, and then additionally where x equals 0. X equals 0 would be this guy right here. So come to find out, taking everything into consideration, that is the region that we need to study. So if that's the region we need to study, I'll go ahead and put a vertical line in there. And you can see the top part would be the parabola. So the parabola would be the y equals 4 minus x squared. The bottom part would be y equals 0. So the bottom part here would just be y equals 0. And then it would scan from x equals 0 to x equals 2. So there's our setup for this particular problem. Now, again, I'll mention it because I mentioned it in the last couple examples as well. Once you get this first part set up, the last two, you're looking back into your two-dimensional region just like you were in the previous sections. So it's really important to get these first two set up, make your decision. In this case, it was decided for us we needed to be DZ to start, but once we have that in play, then when we get this region put together, it's really just going to be the same thing that you've done many, many times.